Swayam Prabha. Digital India. Educated India.
What was the answer? Yeah, you are saying gamma wave equal to A1 dash plus 2 E dash or double dash? I think E dash. Just because there is a 2 outside does not mean it will become E double dash. 2 E dash plus A2 double dash. Okay, you got this? For what? For D3H. Not only for D3H, for something like BF3, CO3, what is CO3 2 minus, so on and so forth. Alright. So, you think you can get it using the formula I wrote? Let us see, we will take some other molecule also, but let us proceed further. Now, I do not want to stop here, but what I want to do now is that I want to proceed a little further. We will not be able to go to the end of this vibrational spectroscopy, unfortunately, then I cannot teach anything else. But let us see if it is possible for us to try to ascribe the actual molecular motion to some of these symmetry species. Let us see if we can go at least one step forward. What I am saying is that in water you know what the normal modes look like, and we started this exercise by saying, is it possible for us to develop a method by which we will be able to tell what the normal modes of BF3 look like? That is what we are trying to do, isn't it? So, let us see if we can go one step ahead in that direction at least. Okay. What are the internal motions of the molecule that are involved in vibration for BF3, for example? You have bonds and you have bond angles. So, what are the different motions that you have? Stretch, the bonds can stretch, right? So, this is plus, this is minus, and bend, there can be two kinds of bends. One is in plane and the other, as we discussed, doming motion, right. So, which is which? Which is which? That is what we want to find out. Let us see if we can do that. So, what we do is we first separate the out of plane motion and the in plane motion. What happened? Out of plane motion and in plane motion. Okay. Let me draw the out of plane motion first, okay, because it is one of a kind, isn't it? So, it is likely to belong to some one dimensional symmetry species. It is difficult for it to mix with anything else. So, let us see. So, out of plane motion how did we draw it? So, I can say this is plus and all these are minus. What does that mean? There is a delocalization of charge from the B atom to the fluorine atoms. So, the fluorine atoms become all negatively charged and B becomes positively charged. We are talking about vibration here, no question of charge. Plus means this atom is coming and trying to hit you, and minus means these atoms are scared of you and are running away from you. Right now they are in the plane, this atom gets curious and comes towards you, it wants to see what exactly you are made up of, and these 3 atoms have had enough and they are running away. That is the meaning of plus and minus here, isn't it? Plus means out of plane motion towards me, minus means out of plane motion away from me. Alright, we are talking about vibration. Okay, got it, everybody got it. Hey, I forgot the name again, Sumit, got it, sure. Okay, so I call this the plus phase, okay, I will call it say plus xi. What will minus xi be? What will the minus phase be? Just replace the minuses by the pluses and the other way around. So this becomes minus, these 3 become plus. Okay. Now the fluorine atoms are inquisitive and they are coming towards you, and the boron atom has had enough and running away. Okay. So this is plus, this is minus. Now can we apply the symmetry operations and see what the characters will be? Let us see. What are the symmetry operations? E, then 2C3, just C3 is enough, then sigma H, then 3C2, oh 3C2 comes earlier, isn't it? Sigma H, then 2S3, then sigma V. How many? 3. What will be the character of E? Of course 1. If I apply C3, then what happens? What should the character be, plus or minus? Do not forget this is plus, the whole thing is plus, this whole thing is minus. So if I apply C3, what happens? The minuses remain minus, right? Wherever you have minus sign now, you have a minus sign even after applying C3. Wherever you have plus sign now, you have plus sign after applying C3. So you agree with me that it is plus xi remains plus xi and minus xi remains minus xi, agreed? Very simple. Huh? So character is 1. If there is a question, please ask. That is what we are saying. You apply C3, what happens? Apply C3 here. This is what you get. It is true that the atoms change place, but the motion as a whole, that does not change phase, isn't it? So this is plus, this is plus, and this is minus. So in plus phase, if you apply C3, what happens? These change place, fine, but plus remains plus. See, the thing is we are facing opposite directions, no? So what is plus for you is minus for me. All right? Okay, whatever it is, let us say this is plus. I understand what you are saying. Okay, let us say this is minus. All right, you apply C3, this is what you get. Hey, what are you not seeing now? All right? So minus remains minus, this is minus, this is also minus. Okay, minus does not become plus by C3, does it? No. So what about C2? What happens when you apply C2? Let us see. Now these are situations where I wish I had one more hand. Where will the C2 be? Achha, don't forget what we had said in the last class. We are talking about simple harmonic motion, which means very small displacement, right? Very small displacement. Otherwise, if this is really as big a displacement as I have shown here, then what would happen? It would not remain a D3H group anymore, it would have become C3V. Okay. So the only reason why we can carry out this discussion is that we are talking about simple harmonic oscillation, which means very small maximum displacement. Okay, where is C2 then? This is C2, agree? If you turn by C2, what happens? Minus becomes plus, plus becomes minus, no? Right, this is plus, this is C2, apply C2, it becomes minus. Another hand would have really helped. Got it, everybody? Convinced? So I will write plus 1, minus 1. After saying all this, if I write plus 1, then what is the point of discussing so much? Sigma h minus 1, S3 minus 1, where the sigma h operation is involved, sigma v is plus 1, isn't it? Okay, now let us compare with the character table. Right. What is this? Remember 1 1 minus 1 minus 1 minus 1 1. Do I need to compare with the character table? Looking at this A1 dash, A2 double dash. The only two options are there, right? A1 dash and A2 double dash. A1 dash means totally symmetric. And A2 double dash, what is the meaning of double dash? Yeah, double dash means it is antisymmetric with respect to sigma h. This is definitely antisymmetric with respect to sigma h. So even without character table, looking at character table, I can say that this A2 double dash mode has to be the doming mode, isn't it? Understood? So I don't even have to look at the character table in this case. Just because it is double dashed, I can say that it has to be the out of plane motion. A2 double dash is 1 1 minus 1 minus 1 minus 1 1. So perfect match, that is what it is. So what we have identified so far is that this doming motion that we could draw easily without much hassle, we have identified that the doming motion, this is like titration. You get impatient at the end point and then it is gone. So what we are saying is that the out of plane doming motion, what is the other famous, what does OUP stand for? What is this famous? Yeah. That definitely has A2 double dash symmetry. So one is assigned. Okay? One is assigned already. What are we left with? A1 dash and 2E dashed. So 3 normal modes, isn't it? Is there a yes or is there a no? What is this? Yes or no? A1 dashed plus 2E dashed, that is 3 normal modes or what? 5 normal modes. So that is a no. That should be a no. 5 normal modes. Don't forget that each E dashed is 2 normal modes. Okay, 2 dimensional representation. So one is assigned, and so what I can write further is gamma vib in plane has to be A1 dashed plus 2E dashed. Because the only kind of out of plane motion is already accounted for. So none of these is antisymmetric with respect to sigma h. So these, whatever normal mode you have belonging to these symmetry species, all these normal modes must be symmetric with respect to sigma h. If they are symmetric with respect to sigma h, then they cannot be out of plane, isn't it? Because if they go out of plane, automatically if you apply this plane, then it has to change sign. Alright. So the remaining 5 normal modes have to be in plane. So that is the second information that we have got. Yes, sure. See, what do we have left now? A1 dash plus 2E dashed. What will be the character of sigma h for these? Okay, E dash I understand is a little problematic, but A1 dash is totally symmetric. So character of sigma h has to be plus 1. Even for E dash, the thing is that dash should give you the hint. Since it is dashed, that means no matter what you do, it is symmetric with respect to sigma h. If it was antisymmetric or if it was not symmetric with respect to sigma h, then it would have been E double dash, right. So, and what I am saying is that anything that goes out of plane, that has to be antisymmetric with respect to sigma h. So, we conclude that A1 dash plus E2 dash, all these normal modes of vibration have to be in plane motion, alright. What are the different in plane motions you can have? Stretch and bend. So, what I will do now is I should construct reducible representations using the bond lengths and the bond angles. What is the meaning of stretch? Change in bond length. What is the meaning of bend? Change in bond angle, right. So, this is what I will do. Let me call this, what do I want to call this? I will call this R1, R2, R3, okay, and I will call these theta 1, theta 2, theta 3. Of course, when nothing takes place, then R1 equal to R2 equal to R3 and theta equal to theta 2 equal to theta 1 equal to theta 2 equal to theta 3. These are the mean positions, alright. Now, once again let me write down this E 2C3, then 3C2, how many sigma h? 1. Can I have more than one sigma h in some molecule? Platonic solids, yes. Octahedral, what about octahedron? Principal axis sigma h, but there are 3 principal axes, right. So, there can be more than one sigma h also for Platonic solids only, okay. Sigma h, then 2s3, then 3 sigma h, then 3 sigma v. I was just congratulating myself thinking that I have been able to write a line without messing up. You should never congratulate yourself, okay. This is what it is. Now, what I want now is I want to write gamma R1, R2, R3. So, E, what will be the character of E? There are 3, no, R1, R2, R3. Now, they are separate, stretching. So, this can stretch and this cannot stretch. So, these are 3 dimensional bases, isn't it? When I have R1, R2, R3, isn't it a 3 dimensional basis? Right or wrong? Huh? Earlier what I was saying is that they are all moving together. The doming motion, all the 3 bonds were moving together like this, right. This correlated motion, that is why it was considered to be 1, isn't it? Right or wrong? Out of plane motion, you cannot have an out of plane motion like this. Why? Why not? Center of gravity will move, isn't it? Symmetry is a small motion, but can you have just one thing moving like this? That will not be a pure vibration, right. For pure vibration, all 3 have to move, because what is happening is, see, remember I had drawn 4 signs, right. When these were plus, this was minus, that means all the atoms were moving. These 3 atoms were moving towards you and the central atom was moving away from you or the other way around. So, thereby keeping the center of gravity in its place. If center of gravity moves, what kind of motion is it? Translation. Of course, this is not pure translation also. So, this is a mixture of translation and vibration, right. So, center of gravity has to be kept in the same place if you are to talk about a pure normal mode of vibration. Do not forget that, okay. That is why this was one motion, the whole thing is one motion. Now, what we are saying is, this can stretch, right, and then the whole thing can go down, no issue, okay. This atom moves out and then these 3 atoms move down. So, that center of gravity will not move then, right. But effectively what will happen is, only this bond length will change, these 2 bond lengths will not change, that is possible, right. This atom moves out and the central atom moves in, right. Yeah. So, that can happen for each of these atoms, each of these bonds. So, R1, R2, R3, these are 3 separate bond lengths and they form a 3-dimensional basis, understood. So, I want to draw write matrices like this, R1, R2, R3 gives me R1 dashed, R2 dashed, R3 dash, okay. So, then what will be the character of 3 of E, sorry, that is a Freudian slip. What will be the character of C3? What happens when you apply C3? R1 becomes R2, R2 becomes R3, right, R3 becomes R1, okay. So, what is R1 dashed? R1 dashed is R2, isn't it? So, what will the matrix? 0 1 0. What is R2 dashed? R3. So, 0 0 1. What is R3 dashed? R1. So, 1 0 0. What is the character? Why is the character 0? Because once again the rolling stone gathers no moss. Rolling stones gather no moss. Earlier you remember the atoms that moved did not contribute to the character. Here also the bonds that move do not contribute to the character because they go off diagonal, right, understood. I do not need to draw the matrices anymore after this. Just remember what we learned earlier. We learned that if something moves from its place, then it does not contribute to the character because it goes off diagonal in the transformation matrix. Understood? Clear? Crystal? Then tell me what is the character of C3? What about C2? If you apply C2 along R1 for example, then R2 and R3 change places, R1 remains where it is. So, R1 does not move, right. So, something that does not move has some character. Here also something that does not move has character, contributes to the character, okay. So, what is the character then? 1 sigma h 3, do you agree? 3, because R1 remains R1, R2 remains R2, R3 remains R3, 3, S3, see in the for S3 first of all you have to apply C3, no. The moment you apply C3, R1 goes to R2, R2 goes to R3, R3 goes to R1, and then when you reflect by sigma h there is no further change. So, they once again they go off diagonal. So, a character of S3 is the same as character of C3 here. So, 0 and what about sigma v? 1 once again without much ado. So, see your representation is also nicely symmetric. It is not symmetric really, it is repetitive. It has kind of crystal symmetry 301 301, right, 301 301, okay. This is gamma theta. If with the thetas now if we do the same operation, what will be the character of E? That even I know. Even I know that it is going to be 3, better be 3, right, 3 or not 3, 3, theta 1, theta 2, theta 3, once again 3-dimensional representation. What about C3? When you apply C3, 0, do we agree? Theta 1 goes to theta 2, theta 2 goes to theta 3, theta 3 goes to theta 1, so 0. C2, what about C2? It is 1. Because see, if you apply C2 along this, okay, theta 1, theta 3 interchange, theta 2 remains theta 2, no? It is just the angle. It does not matter whether it is between R1 and R2 or whether it is between R2 and R1. It is same. Nature loves symmetry, you cannot do anything. 301 again, right? It's as exciting as playing housey. What about sigma h? 3, S3, 0, 3 sigma v, sigma v again 1, right? Because once again you apply sigma v, theta 1, theta 3 will interchange, theta 2 will not. It is not a black and white camera. Why can we not differentiate between black and red? Anyway, this is 1, 301, 301. So now what is the next step? I have to break this down, break these reducible representations down into constituent irreducible representations. How will I do it? AJ or AI, what did I say? AI equal to 1 by H sum over R, chi of R, yeah, chi I of R, very good. You can do it, but even before you do it, do you anticipate a problem? I anticipate a problem. What is the problem? See, what is this? Character of E, right? What is the character of E? If you remember, character of E is equal to the dimensionality. Okay? This also is dimensionality. So, when you break this down, you should get either 3 one-dimensional representations or one one-dimensional representation plus one two-dimensional representation. Okay, same here. All right. So, total dimensionality here is 6. What is the total dimensionality here? 5. So, out of the blue, you have got an extra dimensionality. This is what is called a redundant coordinate. We will come back to that. First, can you please break it down? You need to see the character table. Should I project the character table? First take this, this you can remember, right? 301, 301, very easy. Three zero one, 301, break it down quickly. What is it? A1 prime plus E prime, very good. If I were you, I would have perhaps guessed it. It cannot be anything other than sums of A1 prime and E prime anyway, right? So, see, now the problem is this gives you A1 prime plus E prime, this also gives you A1 prime plus E prime. So, we have an extra coordinate, we do not have two A1 primes, E prime is fine, but we have an extra A1 prime. Where has this extra spurious redundant A1 prime come from? So, what he is saying is that the three bond lengths are completely independent of each other. They can, the length of one is not dependent on the other, very good. But the thing is, since this is in plane, if they are out of plane it would have been fine. Since we are working inside a plane, this theta 1, theta 2 and theta 3 are not independent of each other, right? Only theta 1 and theta 2 should be independent, theta 3 should be dependent, because theta 3 is equal to 360 degrees minus, yeah, theta 1 plus theta 2 in brackets. So, that is where the spurious coordinate has come from. So, what I am trying to say is that this A1 dash that we get from gamma theta, this is a redundant coordinate. And you can identify the redundant coordinate pretty easily, because what does A1 dash mean? A1 dash is a totally symmetric representation, right? Now, is it possible that all these angles will increase? So, what is plus, what is minus in this case? Increase is plus, decrease is minus, right? So, if this A1 dash is really to be there, then what we are saying is that all the bond angles should be able to expand at the same time. That is not possible. If two bond angles expand, the third has to contract. So, A1 dash is just not possible. right. So, what you could perhaps do is work with theta 1 and theta 2 only, that will be a 2 dimensional representation, you work it out, you will see you will get E dashed. Okay. So, what have we learnt so far? We have learnt that A2 double dashed is the out of plane motion. We have learnt that this A1 dashed is a symmetric stretch. So, at least two of these normal modes can be identified unambiguously, right? Yes, sir. Yeah. Yes. That is the problem. That is why we actually work with theta 1, theta 2, theta 3. That is actually a problem. So, but in any case it should become E dashed, isn't it? Because we are working only with character. Then we have got a problem. So, that is why we work with theta 1, theta 2, theta 3 and eliminate the redundant coordinate this way. Alright, fine. So, what have we learned? We learned that A2 double dashed is unambiguously the out of plane doming motion. We have learned that the A1 dashed mode is unambiguously the symmetric stretch. What is left? The two E dashed modes, these have to be combinations of stretch and in plane angular deformation. Right. So, we have been able to go some distance further, isn't it? Now, if we can actually go all the way and we can say that this is exactly this kind of mode. For that, we need to convert this whole problem into what are called symmetry coordinates, and we need to discuss Wilson's F and G matrices. The problem is, if I want to do that, that will take us to the end of the course. So, we do not want to do that, we want to do one more thing about vibrations, and that is IR and Raman activity.